So imagine trying to teach someone a really complex board game. You go through all the rules, and you realize later that they just memorized the specific moves you showed them.
Right, like they memorize that one specific scenario.
Exactly. They have absolutely no idea how to actually play the game. They can mimic you perfectly, but, the second the board changes even a little bit, they just freeze.
It's incredibly frustrating.
It is. And that super frustrating human experience is actually exactly what is happening to the world's smartest AI models right now.
Yeah, on a massive scale.
Right. So today we are doing a deep dive into a brand new foundational paper. It's from researchers at the University of Science and Technology of China, Peking University, and Dartmouth.
And it's called ARMOR, Stabilizing On-Policy LLM-RL with Off-Policy Anchor Samples.
Which is a mouthful, I know. But we are essentially looking under the hood of the exact mathematical reasoning engines that power, like advanced models think OpenAI O1 and DeepSeek R1.
We want to understand this massive, somewhat invisible hurdle in training them?
Yeah, and how this new ARMOR framework elegantly solves it to make AI just, much smarter and more reliable for you.
It's a really fascinating look at the limits of artificial intelligence, honestly, because we often think we're, like, teaching a machine how to reason.
Right, how to actually think through a multi-step problem.
Exactly. But it turns out the machine is often just finding these brilliant but incredibly fragile ways to just memorize the test.
And that really sets up the core problem the ARMOR paper is trying to address, right?
Yeah, because as these models scale up to handle harder, longer horizon reasoning tasks, they actually run a huge risk. They risk literally forgetting how to think.
Okay, let's unpack this from the ground up. Because to understand the problem, we first have to look at how these models learn advanced math in the first place.
Right, using reinforcement learning.
Which makes sense. I mean, math is the perfect training ground for AI because the answer is definitively right or wrong.
There's no gray area.
Exactly. You give the AI a calculus problem. If it gets it right, it gets a verifiable reward. If it's wrong, it gets nothing.
So theoretically, it should just keep getting better and better at math the more you reward it.
Right, that's the logical assumption
Yeah.
for sure. You reward correctness, so general reasoning should just organically improve.
And during the training phase, it really looks like it does. If you look at the training data, the reward curve goes up steadily. The model gets the answers right more and more often.
But, and this leads us to the paper's first major finding, there's this phenomenon known as over-optimization.
Yeah. Paradoxically, if you take that seemingly successful model, the one that's acing the training, and you test its validation performance.
Meaning you give it brand new, unseen math problems to test if it can actually generalize.
Right. If you do that, the performance peaks early on, and then it just completely crashes.
Oh, wow. So it's like a student studying for a math test by perfectly memorizing the practice exam's answer key.
That's a perfect analogy, actually.
They take that practice test over and over. They score 100%. The training reward is perfectly stable. But then they sit down for the real exam, and they fail miserably.
Because they never actually learned the underlying algebraic formulas.
Right. They just learn the shortcuts for the practice questions. But wait, I have to push back here for a second.
Sure, go ahead.
Usually, when we talk about AI reward hacking, it means the reward system itself was flawed. Like, if you tell a cleaning robot to sweep up dust, it might just dump dust on the floor so it can keep sweeping it up and getting points.
Right, the classic specificated in gaming problem.
Exactly. But math is objectively right or wrong.
Yeah.
The reward system isn't flawed. So how can the AI cheat at math?
So that's a critical distinction the researchers highlight. The reward signal in mathematical reinforcement learning is perfectly consistent. I mean, correct is correct.
Right.
So the failure here isn't traditional reward hacking. It's actually a fundamental breakdown in generalization. The AI collapses onto a very narrow set of what they call shortcut patterns.
Okay, so what does a shortcut pattern even look like for an AI doing math?
Well, imagine the model realizes that for a specific subset of, say, geometry problems in its training data, the answer is usually 0 or pi.
Okay.
Instead of actually doing the complex geometric proofs to arrive at that answer, it learns a superficial pattern. Like if it sees a certain phrasing in the prompt, it just generates a bunch of semi-plausible mathematical jargon and then just slaps pi at the end.
Wow, really? So it's just faking the work.
Yeah. And in the training environment, this weird, fragile path yields high rewards because it got the right answer. but it's utterly useless when applied to novel problems.
That is wild.
Right. So in this regime, a perfectly stable rising training reward curve isn't actually a sign of success. It's a blaring warning sign that the model is actively losing its general reasoning capabilities.
So the AI is basically obsessing over a few neat tricks that only work on the homework it's already seen, and it's literally forgetting how to think broadly.
Exactly.
And because the AI is finding these detrimental shortcuts, engineers historically tried to step in and put up guardrails, right?
Yeah, they try to penalize the model for straying too far from its original, more balanced behavior.
Which brings us to the traditional algorithmic defense against this over-optimization. A method called reverse KL regularization.
Which is essentially just a passive penalty system.
Right. And passive meaning you keep a copy of a reference model like, say, a slightly older stable version of the AI, and you constantly compare your actively learning AI to it.
Exactly.
So if the learning AI starts acting too weird or giving answers that the reference model wouldn't give, it gets slapped with a penalty.
What's fascinating here is how meticulously the paper breaks down why the standard defense fails completely in advanced reasoning tasks.
Yeah, the researchers' empirical analysis shows that this KL regularization suffers from two intrinsic structural limitations. And it all depends on, well, how tightly you tune that penalty dial.
Right. So let's look at the first failure road. When the standard penalty is relatively loose, this leads to profound instability.
Which sounds a bit counterintuitive. I mean, why does a loose penalty make it unstable? If the guardrails are wide, should the AI just have room to explore?
You would think so, but reverse KL regularization is mathematically mode-seeking.
Okay, can we translate mode seeking into plain terms?
Sure. It basically means the penalty only punishes the AI for generating highly unlikely or bizarre answers compared to their reference model.
Okay.
But it does absolutely nothing to punish the AI for forgetting good, diverse solutions.
Nice.
So the AI can still collapse into a narrow subset of those shortcut modes. It loses the broad diversity of reasoning it used to have.
The penalty system just watches it happen?
Yep. Because the AI isn't technically saying anything wrong compared to the reference model. It's just not saying enough right things.
Wow. It's a penalty for doing bad things, but not a penalty for stopping doing good things. That makes total sense.
Right.
But then, as an engineer, my immediate reaction is just to turn the penalty dial all the way up. I mean, if a loose constraint lets the AI get away with being lazy, just make the penalty super strict. Force it to stay close to the reference model.
Well, the researchers tested exactly that. And if you apply an extreme penalty, it just acts as a uniform suppression mechanism on all of the model's behavior.
Oh, meaning it can't do anything new.
Exactly. It leads to the second failure mode, stagnation. You rigidly tether the learning policy to the reference policy.
So it definitely prevents the AI from collapsing into bad shortcuts.
Sure, but it also entirely prevents the AI from doing the exploration necessary to discover new, superior reasoning paths.
Because it can't learn anything new.
Yeah.
Every time it tries to step out of its comfort zone and try a novel mathematical approach, it gets heavily penalized for diverging from the old model.
Right, it gets slacked down.
So to frame this for you, the listener, using the old method, you can either have a chaotic AI that forgets how to think entirely, or a completely stable AI that refuses to learn anything new.
It's a lose-lose situation.
Yeah, a passive penalty is just structurally insufficient. You can't just punish a model into being a genius.
And that realization is really the turning point of the Armor paper. Passive punishments completely fail to balance stability and exploration. It's what the authors call the stability-plasticity dilemma.
Meaning you need the plasticity to learn new things, but the stability to not forget the basics.
Exactly. So to solve this, the researchers had to shift the entire paradigm from passive penalties to active stabilization.
Which introduces the first half of their solution, Armor. And the AR stands for anchor rollout.
Right.
So instead of relying on an invisible loss penalty to keep the AI on track, Armor actively injects something called off-policy samples from the reference policy directly into the training batch.
Let's clearly define what on-policy and off-policy mean here, because it's central to the whole framework.
Yeah, definitely.
So on-policy refers to the data the AI is generating right now, in the moment, as it attempts to solve a problem. It's the AI's active practice swings.
Okay, and off-policy.
Off-policy refers to data generated by a different, usually older or more stable model, which is the reference policy.
Got it. So during training, the AI generates a batch of attempted responses to a math problem. Those are its on-policy attempts.
Yep.
But with anchor rollout, The system uses rejection sampling to guarantee that alongside the AI's new attempts, there is an auxiliary off-policy anchor sample included in every single batch.
Exactly.
I think rejection sampling is one of those terms that sounds super intimidating, though. How does that actually work mechanically in this context?
Mechanically, it's just a filtering process. Imagine the system generates a batch of, say, 10 possible mathematical reasoning paths for a given problem.
Okay, the 10 active practice swings.
Right. Rejection sampling analyzes that batch and looks for a specific high-quality solution that matches the logic of the stable reference model. That's the anchor.
Oh, I see.
And if the batch doesn't naturally contain that anchor sample, the system literally rejects some of the bad samples and actively injects the correct anchor into the training batch.
Wow. So it mathematically forces the presence of a guaranteed, generalizable, correct solution.
Oh, it does.
So the model is constantly being fed a reminder of what solid, logical reasoning looks like, directly alongside its own current messy attempts.
Exactly.
You know, here's where it gets really interesting for me. Think of it like learning to play jazz.
Okay, I like where this is going.
When you're learning jazz, you want to improvise. You want to try wild new chord progressions and push your boundaries. That's the on-policy exploration phase.
Right.
But if you just improvise without any underlying structure, eventually it just sounds like noise. You completely lose the underlying melody, which is basically mode collapse.
Yep.
So anchor rollout is like having a strict jazz instructor who lets you improvise all you want, but periodically forces you to play the standard scales perfectly.
I love that.
That scale is your anchor. It ensures you never lose your foundational technique, no matter how far out your improvisation gets.
And to push that jazz analogy further, the standard passive penalty like the old KL regularization method would be an instructor who just yells at you every time you play a wrong note. But they never actually show you what the right notes sound like.
Yeah, eventually you just stop improvising entirely out of fear.
Exactly. But anchor rollout actually shows the AI the correct path, and the empirical result of this explicit signal is staggering.
Really?
Yeah. The researchers found that simply injecting this correct anchor sample forces the model to continuously recall and preserve its established generalizable solution patterns. It completely cures the instability and mode collapse. The model no longer forgets how to think because the correct way to think is actively present in its training environment at all times.
That is a huge breakthrough just for stability alone. Yeah. But, while anchor rollout stops the AI from regressing and collapsing, simply surviving isn't the actual goal here.
No, we want the AI to reach unprecedented levels of reasoning. We want it to get significantly smarter.
And that requires the second component of the framework.
Right, because if you look at the paper's ablation studies, which is where the researchers strip away parts of their own framework to see what happens when pieces are missing, they found a clear limitation.
What happens?
If you only use anchor rollout, the training process becomes incredibly stable, but the AI hits a strict performance ceiling. It's safe, but it's constrained. It doesn't surpass its previous capabilities by much.
Which tracks perfectly. I mean, if you just keep making the jazz student play their scales over and over alongside their improvisation, they'll be competent, but they'll never become Miles Davis.
Exactly. So to break through that ceiling, the researchers introduced the MO in ARMOR, mixed optimization.
Okay, let's get into the MO.
So because the training data is now this unique mixture of the AI's new explorative attempts and the established correct anchors, the underlying mathematical objective function used to train the model has to adapt.
It must align with this new reality.
Right. So the researchers fundamentally reformulated the policy objective by modifying the importance sampling ratio. They optimized for a mixed policy rather than just the active policy in isolation.
Okay. Importance sampling ratio is definitely the densest math concept in this paper. Let's demystify this a bit. What does modifying that ratio actually do to the AI's behavior in practice?
Well, in standard reinforcement learning, importance sampling is essentially a mathematical trick. It lets you estimate how good your new policy is by looking at data generated by your old policy.
Okay.
You take a ratio, the probability of the AI making a specific move right now, divided by the probability of the old model making that exact same move.
Right.
If the new AI is doing something wildly different, the numerator gets huge, the ratio blows up, and standard training algorithms clip it. They put up a rigid mathematical fence that says, do not change your behavior more than a few percentage points in any single update.
Oh, so it's literally a mathematical speed limit on how fast the AI can learn something new.
It is, but ARMOR changed the denominator of that ratio. Instead of dividing by just the old policy, the denominator becomes a mixture of the current policy and the anchor policy.
Okay.
The consequence of that is what the authors call an adaptive trust region.
So instead of an invisible electric fence that zaps the AI if it steps too far in any direction, the fence actually moves.
Precisely. The adaptive trust region selectively reinforces verified correctness.
Wait, selectively reinforces.
Yeah. Say the AI takes a massive leap in its reasoning, like it skips 3 steps in a proof because it found a brilliant new angle.
Okay.
If that leap aligns with the underlying correct logic of the anchor sample, the denominator adapts. The ratio stays manageable, and the boundary expands to allow it. It lets the AI take much larger steps toward correct innovative actions.
Oh, wow. He knows when to give the model slack.
Hmm?
But what if the model's huge leap is just a hallucination? Like, what if it's confidently wrong?
Then the adaptive trust region does the exact opposite. It rectifies reference biases.
Meaning it tightens up.
Exactly. If the AI takes a massive step toward an incorrect action, the boundary tightens, allowing the system to heavily penalize that mistake.
Even if the original reference model might have been tricked by it in the past.
Yep. It's a dynamic, context-aware guardrail that gives the AI the freedom to decisively outgrow its past limitations while violently punishing actual logical errors.
Okay, so we have the theoretical brilliance down. Anchor rollout provides the stability floor so the AI doesn't forget the basics.
Right.
And mixed optimization provides the adaptive ceiling to allow for massive exploratory leaps.
Exactly.
But, theory only gets you so far. How does this actually perform in the wild on state-of-the-art models?
The benchmark results are nothing short of massive, honestly. They tested Armor on the Qwen 2.5 Math 7B and Qwen 3 8B base models.
Which are very solid models.
Oh, absolutely. And they applied it on top of standard, highly optimized R algorithms like DPO and QAE, and they didn't just test it on basic arithmetic either.
Right, they use brutal benchmarks, specifically the AME 2024 and 2025.
Yeah.
And just for context, for you listening, the AA is the American Invitational Mathematics Examination. These are tests that challenge the absolute brightest high school math students in the world.
They're incredibly difficult.
They aren't multiple choice. They require multi-step logical leaps, deep algebraic manipulation, and creative geometry. This is the exact kind of test where an AI relying on memorized shortcuts will just spectacularly fail.
And yet, applying Armor made the numbers jump dramatically. Average math scores on these intense AIM benchmarks went up by 5 to 8 points.
Wow.
And on the Qwen 3 model, performance jumped by over 11 points.
Okay, in the context of the AIM, an 11-point jump is astronomical. I mean, these tests are usually out of 15 points total.
Right.
Gaining 11 points isn't an incremental update. It's literally the difference between an average student and a math prodigy. It means the AI is actually sustaining long chains of complex reasoning without losing the plot.
And here is a crucial detail that cannot be overlooked. These massive reasoning gains did not cost the model its general capabilities.
Which happens a lot, right?
Constantly. Often in AI training, there's a phenomenon called catastrophic forgetting. The AI gets so intensely focused on becoming a math genius that it suddenly forgets how to write a poem, or it just loses its ability to answer a basic science question.
Its brain essentially overwrites general knowledge with calculus.
Exactly. But they tested the Armor-trained models on GPQA, which is a graduate-level science benchmark, and MMLU Pro, a massive language understanding test.
And how'd it do?
The performance was fully maintained or even improved. There were no trade-offs. It's a holistic, complete upgrade to the model's foundational reasoning capabilities.
That is incredible. Oh, and looking through the paper's implementation details, there's one really fascinating mechanic regarding the anchor itself, something they call reference reset frequency.
Yeah, that's a really important piece of the puzzle.
Because what happens if you just use the exact same static anchor sample forever?
Well, if you use a static anchor, the AI eventually gets held back by it. It's like pacing yourself against a running partner who never gets any faster. Eventually, you have to slow down your own progress just to stay near them.
Oh, that makes sense.
So the paper details the necessity of periodic resets. For example, they found optimal results by updating the reference policy every 160 training steps.
So the anchor isn't a fixed point in the past. It actually evolves alongside the model.
Exactly. You take the highly capable, newly trained AI, and you make that the new reference anchor. By doing this, the AI is constantly comparing itself to its newly improved self, rather than a stale, outdated baseline from weeks ago.
Wow.
This continuous ratcheting effect is what sustains the performance gains over extended training horizons. It creates this upward spiral of intelligence.
So what does this all mean for you listening to this right now? When we zoom out and look at the trajectory of artificial intelligence today, the whole industry is racing to scale up generative AI to tackle harder, longer horizon reasoning tasks.
Right, think AI scientists, AI software engineers, systems that have to think for hours or even days, not just milliseconds.
Exactly.
Yeah.
And the biggest threat to that future was the AI literally forgetting how to think while blindly chasing high scores in its training environment.
Mm.
Armor proves that we can solve this by decoupling the constraints.
Yeah.
We use anchors to hold the model firmly to reality, and we use mixed optimization to let it safely explore new frontiers of intelligence. This mathematical framework is exactly why the AI tools you use tomorrow are going to be radically more consistent, logical, and capable than the ones you interact with today.
It's a profound shift in how we engineer intelligence. And, this raises an important question to think about. What if human cognitive development operates on a remarkably similar mechanic?
Oh, that's interesting.
Think about your own learning journey, whether in your career, your hobbies, or how you view the world. Do you learn best by rigidly punishing your every mistake and staying exactly where you are? Or do you grow by constantly anchoring yourself to a few indisputable core truths while giving your brain an adaptive trust region to freely explore and challenge everything else?
Wow.
As we teach machines how to reason without losing their minds in a sea of data, we might just be uncovering the optimal mathematical formula for human mastery as well.
What a thought to end on. If you want to dive deeper into the math, the rejection sampling, and the specific ablation studies we discussed, you can find the full paper, Armor, Stabilizing On-Policy LLM RL with Off-Policy Anchor Samples, online. Thank you for joining us on this deep dive into the sources, and we'll see you next time.